Hey guys, so in another video, I frequently use this diagram to find the exact charge of a group. In this video, I will explain why this method works, as well as the relationship between pH and pKa. So when comparing pH and pKa using this method, there are two variables you need to consider. Number one is which side of the pH is the pKa value on, and number two is how far is the pKa from the pH value. Beginning with the first point, the position of pH and pKa is a way to determine which form the species you are analyzing is. So to understand what I mean, we need to first quickly review the concepts of pH and pKa. So beginning with pH, it is equal to the negative log of the proton concentration. For our purposes, we're usually going to use pH to describe the surroundings and how much free hydrogen ions are within it. For example, we'll probably say, what is the pH of the liquid solution, or what is the pH of the water surrounding the amino acid? In relation to acid strength, how acidic something is defined by the H plus concentration. The higher concentration of H plus in the surroundings, the more acidic it is. Because of this, it is tempting to assume that stronger acids, which have higher amounts of H plus, would result in a higher pH value. However, the equation for pH has a negative sign for the side with the H plus variable. This means that there is an inverse relationship between the pH reading and H plus concentration. Overall, this means that the stronger the acid, the lower the pH value. For pKa, it is equal to the negative log of the dissociation constant, which is a value that characterizes the tendency for a species or system to dissociate its hydrogen. This is different from H plus concentration because H plus is something that physically exists, but the Ka is just a characteristic of something. So this value, for our purposes, is gonna usually be used to refer to the system we're interested in. Usually this is just gonna be like the certain group on a amino acid. For example, you'll probably hear me say the pKa value of the amino group or the pKa value of the carboxyl group. Since increasing the H plus will increase the acid strength, the more likely a hydrogen will come off of the system and end up in the surroundings, the stronger the acid. Higher tendency for dissociation means a higher K value. However, just like the pH equation, there's a negative sign, which means K has an inverse relationship with pKa values. Overall, this means that the lower the pKa value, the more acidic that species or system is. Now that we have a basic understanding of pH and pKa, as well as how their value corresponds with acid strength, we can now compare the two. So, if pKa is lower than the pH, then that means the system is more acidic than the surroundings. As the stronger acid, it will be stronger in its abilities to move H plus ions from itself into the surroundings. An example would be like a carboxyl group in water. The carboxyl group would favor dissociating its H, resulting in an O- and an additional H plus in the environment. In the result, the COO- is considered the basic version because now it does not have its hydrogen anymore. And the COOH present in the beginning is considered the acidic version. This essentially means that if the pKa is lower than the pH, the species will result in its basic version, which I like to call the quote-unquote negative version. If pKa is higher than the pH, it is basically the opposite of what we just saw. The surroundings now have a lower value, so it is considered more acidic than the system. Now, if you imagine from the point of view of the surroundings, it now has a stronger tendency to associate its H plus ions onto the system because now the system is considered basic, which is just another way of saying less acidic. An example that shows this would be an amine group in water. Since the water pH of 7 is lower than the pKa of 9-ish, what happens is that the H plus in the surroundings will now be a part of the system by bonding to the group. NH2 becomes NH3 plus. NH2 is considered the basic version because it has no charge and less hydrogens, and the NH3 plus is considered the acidic version because it has the positive charge as well as more hydrogens now. So overall, if the pKa is higher than the pH, that means the system will result in its acidic version, which I like to call the quote-unquote positive version. Now that we know why the position of pKa relative to pH impacts the kind of charge the species takes, we need to now understand how the distance between the variables influences the magnitude of the charge. For this, it's best explained by looking at a titration curve. So over here, this curve details the titration of glycine, an amino acid that only has two ionizable species, which are its carboxyl and amino group. The y-axis details pH level, and the x-axis details how many equivalents of base there are. This might be a little confusing, but the OH minus in the brackets simply means how many base forms of the system are present in the solution. So a best way to understand this is to just look at the very far right of the x-axis. Since there are only two ionizable groups on the glycine, the amino and the carboxyl group, the max of the x-axis would be 2, which is where all the groups are in their basic form. And looking at the far left, the minimum is 0, which means none of the groups are in their basic form. So I always use a magnitude of plus or minus 2 to determine full charge, because looking at this graph, when the pH is 2 units away from the pKa, pretty much 100% of the group is at a whole number equivalent, meaning the entire group is in either a basic or acidic form. And when it is less than 2 units away, it is in what we call the buffer region, which results in the group only having a partial charge. At that point, you would have to use the Henderson-Hasselbalch equation to find the exact partial charge. For example, let's look at the carboxyl group, which has a pKa of 2.34. If we were to go 2 pH units away from it, we see that the species now has almost entirely one equivalent of base. Looking at the above illustrations, we also see that one full equivalent of base means that COOH has now become its basic form, which is COO minus, while the amine group is still in its acidic group. So when we go 2 pH units away in the other direction, we see that the graph tells us there's pretty much no equivalence of base in the solution, which makes sense because at that point, looking at the illustrations, both the amino and the carboxyl group are in their acidic forms. Now, if we go less than one equivalent away, we end up in a region between 0 and 1 equivalent of base. Again, this is the buffer region, which means that the pH and pKa values are too similar for either of the acid or base forms of the carboxyl group to dominate. So the only way to exactly determine the proportions of each forms that exist, we would have to use the Henderson-Hasselbalch equation. All right, so looking at these titration curves, we can now conclude that if the pH units are 2 units away from the pKa, the species will take on their full acid or base forms, which I like to call quote-unquote plus or minus forms. Now, if they're within, they'll take on partial forms, which basically means it'll have a partial charge. Combining this concept with what was said earlier about the positions of pH and pKa, we can now combine them together to finally get this model to determine charge.